Oh, good stuff. Electronegativity day. So, yeah, I think we talked a little bit about some things here, but the nucleus of an atom is positively charged and therefore attracts electrons, which are negatively charged. If you wanted to kind of simplify this definition right here, all right, I'd probably say, like, it's the ability of an atom to attract electrons, its own, and as well as other ones as well. So how well does it attract electrons or want to gain electrons, basically, or how well does it pull electrons towards itself? Okay. We talked a little bit about, which one actually, which atom does have the best electronegativity. You might want to get a periodic table. Anyone? Yeah, fluorine, right? Which one has the, well, this is kind of a trick question, I guess, in a couple ways. Which one has the worst? Yep. Noble gases, and then if it was actually not the noble gases, which one? Francium, okay? So, yeah, noble gases, of course, don't really want to attract electrons. They already have their full set energy level for the most part. As you get farther down, there is some numbers. Don't worry about that, okay? Higher electronegativities include a greater attraction for electrons. Electronegativities increase as you move across the period. So when you go from metals basically to non-metals, they increase in electronegativity, generally speaking, of course. And if you move down the group, they decrease, okay? So basically, yeah, francium in the bottom left corner is going to be the worst. Fluorine is going to be the best, okay? And then, of course, the noble gases are usually not applicable. Noble gases do not have EN values as they do not naturally form bonds. Yes, true. Okay. Now, did we copy this? Did we get to this part? No, we didn't get to the lithium and fluorine, did we? No. Okay, but the size of a neutral atom will actually decrease from left to right across the period. Because of the atomic number, you might think the opposite. Okay, we're not going to worry about this part here. Don't worry about that. Did we copy that part or no? Okay, we're good there. Okay, well, I'll stop and you guys copy. So I'm just, we kind of talked about that neutral atom, etc. But let's just draw this here. So basically what they're saying here is this. If you took lithium, which is 3 protons, we're going to draw this 4 neutrons. And we got, there's the nucleus, of course. There's my 2 electrons. And there's my 1. Okay. And that's an example of what lithium looks like, of course. That's in period 2, which is you guys. No way. All right. Nothing. Okay. Well, you know what? And then we're going to go over all the way. So we're going to go through lithium. What's next? Beryllium, boron, carbon, nitrogen, oxygen. When we get to fluorine. Fluorine, okay, has 9 protons and 10 neutrons. It's got 2. And it's got a second energy level, and it looks a little something like this here, right? We know that from previous drawings. There's a Bohr diagram of fluorine. And what the notes basically tell you is that the atomic size, okay, the atomic size, the atom size actually condenses here. Now, if I asked you between these 2 atoms here, lithium and fluorine, which one is bigger? All right, and I just said that, big, which one's bigger? Most of you would probably pick what? Fluorine, yes? Which one's bigger? Well, that's kind of a misleading statement. I guess if I said which one weighs more, you would say, this is not a trick question, which one weighs more? Fluorine, yes? Weighs 19, by the way. Lithium, of course, weighs 7, yes? But if I said which one actually is physically larger, or which one actually takes up more space, if we were looking at these 2 atoms, the answer is actually lithium, okay? Fluorine is actually a smaller atom, and we say that the atomic size is actually decreased. It's actually sucked together a little bit more. So in this case here, we have 3 protons that attract 3 electrons, right? So we have to think about how many positives and how many negatives are there. 3 positives, 3 negatives. I guess we could do a little fancy math and probably say like there's about maybe, each proton attracts 3 electrons. So what is there? 3, 6, maybe 9 attractions altogether kind of thing. all right? But these protons right here, of course, these 3 protons have to attract these 3 electrons. And, you know, it does that pretty well, but there's only 3 positives, 3 negatives. When we go over to fluorine, you'll notice we have the exact same number of energy levels, don't we? First energy level, second energy level, first energy, second energy level. Now we have 9 positives, and they attract these 9 electrons, yes? Okay, so because of that, there's 9 positives attracting 9 negatives. What happens as we go across the periodic table from left to right, what happens is the atom size gets shrunk down a little bit. So we start to see the atoms start to kind of condense, if you want. They get sucked in a little bit more and 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 a little bit more. It's not huge, but there is a difference. Okay, generally speaking, as we move from left to right, the atom size, not the weight, there's no doubt about that, the atom size actually starts to decrease. And that's important for electronegativity because which one is better at attracting extra electrons? This one here? Not really, right? If anything, this one wants to get rid of it, lithium. But this one here, the atom size is going to be even smaller. And if we're going to talk about atom size, we sometimes talk about this part right here. What do you think that's called? The atomic from the middle to the outside. You guys know this from math. Atomic from the middle of the circle to the outside of the circle. We're in grade 11. Yeah, we're in grade 11 now, so you should know the term radius. Yes. So that would be the atomic radius. Okay. That atomic radius is going to be less than the atomic radius here. Okay. That's going to be farther. All right. So the atomic, you could say atomic size or / radius decreases. Okay. So the atomic size or the atomic radius decreases as you move across a period. The protons, 9 protons are attracting 9 electrons. There's a lot of opposites attract there, and it's helping suck that atom in. Okay, and if we looked at electronegativity values, by the way, this is, I want to say 1. Is that correct? Help me out here. And this is, of course, 4. Okay, so that will help increase our ability to attract electrons and also other electrons as well. Okay, we're going to look at a little diagram here right away. Good? Is it 1? Yeah, 1.0. Okay. All right. So this happens across all the periods, basically, and it's a general statement. So there might be some, especially in the 3 to 12 transition metals, where that might not be quite true. But for the most part, as we go across left to right, the atomic size is getting smaller. The atomic weight goes up, though. Yes, there's no doubt about that, because more protons and neutrons it weighs more, but it's actually a smaller atom. Okay, it gets sucked in. Good. Okay. Now, I don't know if you really need to. Yeah, we'll copy the top part here. Let's copy this, and then we're going to do lithium and sodium here real quick, and I'll just stop this here. Now, if you move down the group, okay, so we talked about going across a period, that's fine. If you move down the group, though, there's no tricks here. Basically, lithium, of course, we know looks like this. Lithium is 3 protons and 4 neutrons, and it's got your 2 here and your 1 here kind of thing. That's all fine. And then if we go down to sodium, you might say, well, geez, sodium's got a lot more protons, 11 protons and 12 neutrons, and it's got 2 and 1, 2, 3, 4, 5, 6, 7, 8, and 1 out here. And you might say, well, which one weighs more? Obviously, sodium, no doubt about it. Which one is a bigger physical sized atom, or which one has a larger atomic radius, or which one has a larger atom size? And again, there's no tricks here. Look, this might have 11 protons and 11 electrons, but this only has 2 energy levels, right? This one has 3. And there's no comparison between those two. 3 energy levels is physically going to be bigger, yes? Okay. So 3 energy, like having 3 energy levels, that's just bigger. right? We've got to go an extra energy level to get to the other electron there. It was different before because they were both 2 energy levels, and then we had more protons, electrons. This one has 2 and then 3, so the 3, of course, is a larger atom. There's no doubt about that, okay? And that's why, okay, and actually this is why, as we go down here, you know, if we think about lithium, here's sodium. I'm going to move it down here, actually. You know, if you think about francium, you know, think about, again, francium is what? I think it's 87 protons. I don't remember how many neutrons it has, but it's got 87 protons. You need to have 87 electrons. So think about that. There's 2. Don't have to draw this one, by the way. 8. I'm just going to show you something. 8. What comes next? Well, just for simplicity's sake, obviously, and we don't know this, and we're not going to learn this year, but I'm going to go 2, 8, 8. Oops, I missed one here, didn't I? 8. This has actually got 18, okay? Then there's another energy level with 18, I believe. Is that right? Yeah. And then we get to the 36. And I think that's what, 72, 80. Oh, I went too far, I think, on one here, didn't I? 2, 8, 8, 18, 18. Oh, that's right. 36 and 1. That should, I don't know. Hopefully that adds up to, it should add up to 87. I don't know if it does or not. It seems like I got too many there. Anyway, the point is it's really big, okay? And how well do those protons in the middle attract all the electrons on the outside? Look how far it is from here to there, yes, to attract that 1 electron. So how well is it going to hold on to that electron? Not very well. And that's why it's so reactive, yes? Because anything that comes along, francium's not going to be able to hold on to that electron. It's going to lose it very quickly, yes? Okay? So that's why it's very reactive, yes? Okay? All right, moving on here. Okay, you don't have to copy this. This is in Google Classroom if you do want a picture, but here's kind of the idea, all right? So here is an example of cesium. Cesium's a pretty big atom, and that's the nucleus, okay? So basically what they're trying to show you here is how well does cesium have an effect on silicon, or vice versa, how well does silicon affect cesium? Well, again, okay, the closest this nucleus is ever going to get to any other electrons, including its own, is that far, yes? That's as far as it's going to, you know, that's as close as it's ever going to get to that other atom, basically, to gain those electrons, yeah? And so the distance there is, of course, you might say, well, that's not very big, but of course, you know, it isn't, but it's quite large in comparison, yes? But because fluorine, you know, comparatively speaking, is very, very tiny. In fact, it's one of the tiniest atoms, you know, generally speaking, when we talk about gaining electrons. So how well do the protons here attract not only its own, but the valence electrons here? The answer is pretty good, right? Pretty darn good, because that distance is not very far. So it can attract those electrons or do whatever it wants with them fairly easily, yes? Okay, and that's what it talks about here. Valence electrons of silicon can get much closer to the nucleus of fluorine than to the nucleus of cesium. This is because the attractive force of fluorine acts nucleus on the valence electrons of silicon is much greater than the attractive force of the cesium nucleus on the valence electrons of silicon. So just basically it comes down to a distance thing, okay? All right, so that is important because that's going to kind of tell us what's going on with these different types of bonds or different types of compounds that we have today, all right? So I'm going to get you to copy this, and we're going to go through this, and actually for a little review, because tomorrow you have a test on this, or a little quizzy quiz, I guess we should say, you go ahead and you draw me what sodium chloride, what you think sodium chloride should look like, okay? Just like you're going to do tomorrow. Neutral atoms. So we're going to start with some neutral atoms, yes, which a lot of you did there. So sodium's got 1 valence electron, chlorine has 7, yes. And then we're going to use, what are we using? What do we use? Yeah. Arrow, yeah. Arrow to show the electrons moving, yes. Okay, because it's a metal and non-metal, ionic. And as a result, I don't know what we want to do there. You're going to get what? Sodium that's lost an electron, 1 plus, brackets, don't forget. Okay, and chlorine look like this. And of course, we gained 1, and we're going to get that, right? And that's what an ionic bond is, right? Opposites attract, and they hold each other together, right? I don't want to see any lines between these two because it's ionic. Now, yeah, good? Okay. I think we're going to talk about this right now. So, you might say, let me just check something here real quick. Yeah. Okay, so we're gonna, I mean, this is kind of coming up here, but I just want to do this now while we're here, so we don't, have to go back and forth kind of thing. So let's talk a little bit. How do you know that this is ionic? What would you tell me? If it's ionic compound, it's got to be what? It says right there in the definition, doesn't it? Yeah. Metal and a non-metal, right? Well, yes. Generally speaking, that's true. Metal and non-metal. But let's also talk about something called electronegativity, right? So let's take a look at electronegativity here. Let's write this down. Here's the electronegativity of sodium. And you're going to need your periodic tables up. Yeah, 0.9, right? Huh? 0.9. What's the electronegativity of chlorine? Huh? 3.2. Okay. Now look, we're going to learn something about electronegativity here coming up. But basically, when we look at these two elements here, okay, the difference, and again, we don't know this, but remember, the lowest we can have is what for electronegativity? That may be a trick question again, but what is it? It's 0, right? Kinda. But remember, the 0 ones, the noble gases, they don't want to react with anything else, right? So if we're going to talk about compounds, what's really the lowest then? Yep, 0.7, which of course is francium, yes? So if we think about francium, it's 0.7. Which one's the best again? Fluorine, 4.0, okay? So think about that difference. That's a big difference, isn't it, in electronegativity? That difference is so large that fluorine says, hey, I'm going to take your electrons, I'm going to attract your electrons, and francium's like, there's not much I can do about that, And really what it comes down to, we're going to talk about vectors a little bit, which is physics stuff, yes? But you don't have to freak out because I know you didn't sign up for physics. I get it. No one likes physics. Ugh. Okay? Ugh. He just told me, oh, physics explains everything in the world. Whatever. That's what they do. That's what they tell themselves and their students so that you keep taking that class. Okay, let's be honest. Okay? This class is way better. Just wait till we get to the labs and we blow stuff up, which is applied physics. But basically, we're going to use a little bit of vector, or basically tug-of-war kind of thing. So if you think, hey, in this case, chlorine's pulling with a force of 3.2 that way, and a force of 0.9 this way, which is not to scale, by the way. That's okay. Who's going to win here? Who's winning this tug-of-war, let's say? Chlorine or sodium? Chlorine, yes? So that's what happens with ionic compounds. The non-metal says, hey, I want your electron, and the sodium's like, well, gee, I'm going to put up a little bit of a fight, but in the big scheme of things, chlorine's going to win out here and take that electron to complete its octet. And sodium's not too upset about it because, of course, sodium really doesn't really want that extra electron anyway, right? I mean, it's pulling with a force of 0.9. It's kind of like pretending that it still wants his lunch money, yeah? But really, chlorine's taking the lunch money, yeah? Right? So that's what happens with ionic compounds. And we're going to talk about that coming up here. But that's where we get that large difference. That's when electrons are transferred, okay? And I know the next question, I know you got probably a couple questions coming up here, but just we'll be patient, okay? Good? That's kind of what happens on ionic compounds. All right. Now, we're going to have to copy this, unfortunately, but that's okay. Let's do, yeah, right there. We'll do up to there, and then we'll talk about these one here. But okay, so there's a couple things here going on. First of all, what do you notice about this? Covalent bonds. What does covalent mean? Sharing, yes? So we're sharing electrons in this case. Okay, this only happens when we have two non-metal identical atoms that form a covalent bond. So what does this look like? Well, hydrogen's got one electron, hydrogen's got one electron, okay? And of course, because they're non-metals, we talked about this the other day, non-metals, we'd probably draw it like this, right? H, like so, yeah? Right? H2, okay? And again, it does come down to electronegativities though. Let's talk about electronegativity here real quick. This is 2.2, and so is this one. So this hydrogen's pulling with a force of 2.2, and this hydrogen's pulling with a force of 2.2, right? So what happens if we had a tug of war with this? What happens to the electrons between these two? Do they really go anywhere, kind of thing? No, I mean, obviously electrons are going around and around, but what does this mean really? Okay, they're going around and around, but the electrons definitely are not gonna, could you make a case, well, how do you know this is not ionic compound, Mr. Bachek, HH? Well, first of all, they're sharing electrons, right? And who's got a bigger pull here? Either one, right? In fact, they have the exact same pull, don't they, on those electrons? So not only do they have the same pull, but we're going to say that these electrons are actually going to be shared. Now, this isn't going to make maybe sense yet, but these electrons are going to be shared equally between these two atoms because nobody has a little bit bigger pull than the other one. We're going to talk about that in a second. But if we know that that's the case, nonpolar, okay, nonpolar implies that they're shared equally. Okay, we have to know that. Have to know that. This is shared electrons equally. Shared electrons equally. Okay, nonpolar means basically that they're going to share electrons. The covalent part means, or sorry, nonpolar means equally. Covalent means sharing, yes? So we're sharing equally between the two. And that might not make a lot of sense yet, and that's okay. But after this next one, it should. Okay? Are we clear there? This happens with any molecular element. I have no brighter, clever friends, people stupid, yes? That kind of thing. I2. I'm going to share those electrons equally, yes? Okay? OO, which we don't want to make any mistakes here. Oxygen, OO. We don't want to make any mistakes. I'm trying. It's Monday though. It's not easy. Okay, but OO shares electrons equally. Yes. NN, FF, BR, BR, II, captain, my captain. Okay. Iodine. All right. Those would be the non-polar covalent bonds. That's a long string of stuff. But here's the important thing. Notice the key word bonds, okay? Because tomorrow we're going to switch that a little bit, okay? But today, non-polar bonds. We talked about ionic bonds before this. That was give and take because of a big difference in electronegativity. Non-polar, sharing equally, okay? Bond. Now we're going to talk about what we call a polar covalent bond. I'll let you. All right. Polar covalent bonds. Well, yeah, so in this case here, non-metal with the greater electronegativity tends to pull electrons closer to it. It gains a partial negative charge. While this happens, the other non-metal atom will gain a partial positive charge. They're indicated by those two symbols there, and they are called delta. As a result, electrons that are shared spend more time closer or around the atom with the higher electronegativity. So, you know, for example, if we're going to draw a little HCl, it would look a little something like that, perhaps. Again, I probably wouldn't give you this one tomorrow because this is a little bit of a different one here, but something like CH4 or H2O or something like that tomorrow. And of course, we'd probably draw sharing, yes, in this case here, okay? Now, again, how do you know that you have to draw that or not the other one? Well, again, these are two nonmetals. This is 2.2, by the way, and this is 3.2. So now what it comes down to is, well, this one obviously has a bigger pull than that, correct? Okay. So the one with the higher electronegativity, the one with the wants more electrons, will, yes, kind of gain them. But this is 3.2 and 2.2. So that difference isn't really a large amount of difference, right? And you might already have a question, and that's okay. But it's not a big enough difference for chlorine to say, hey, I want your extra electron, and I'm going to take it from you, because hydrogen's still putting up a decent fight here. So they're kind of like back and forth a little bit, even at this point. They're back and forth a little bit, but because the electrons overall are kind of getting pulled a little bit this way, okay? In other words, they're not sharing them equally because the electronegativities are not the same anymore. We're getting a little bit of what we call a partial negative charge, which we represent with that delta sign. So we gain a little bit of a negative charge there, okay? And as a result, we get a little bit of a positive charge here. In other words, electrons will tend to spend some more time around the more electronegative atom, right? In this case, chlorine. So electrons are negative. They get pulled more to the higher number, of course. So we put on a little bit of a negative charge, okay? The difference here is it's not enough difference to make it ionic. It's not enough to take that electron. They're still sharing them, but we're not sharing them equally, okay? It's kind of like in the sandbox when your mom tells you that you got to play with the other kid and you're like, share the toys, and then you spend most of the time with the toy and you like, and then she says share, and then you kind of like push it over here for a second, and then you take it back and you play with it for the rest of the time. That's kind of what's happening here, right? It's like I'm sharing, right? But they still share electrons. It's just that they're not sharing them very equally between them. More electrons are going to spend more time around the chlorine atom, which makes it that little bit of a negative charge. What's a famous example of this kind of thing here? Which one has a little bit of a negative, a little bit of positive? What's your famous example for that? Not beer. I'm not doing. What's a famous example of a not sharing equally kind of thing? Polar. Yeah, water, right? Water doesn't share those electrons equally, okay? That's another example, okay? So polar basically means this. Let's write this down. Polar. Electrons are not shared equally, okay? And polar basically means not sharing electrons equally, or sorry, not equally, polar, not equally. And then the covalent part means we're sharing electrons, but sharing electrons not equally. Polar electrons are not shared equally. All right? So those are kind of the three main types of bonds that we have going forward. This is important because now we can decide, okay, should this be an ionic compound, molecular compound? Are they sharing electrons equally? Are they sharing them not equally, et cetera, okay? So that'll kind of give you that idea. Yep. So you might say, okay, well, how do I know that? And for the most part, when we talk about metals and non-metals, we're going to pretend that they're ionic, all right? When we talk about two non-metals, we're going to say, well, that's covalent, okay? Maybe we can kind of narrow it down a little bit, polar covalent or non-polar covalent bond, but, you know, we're still going to stick with that for the most part. How do we determine bond types, okay? And all I want you to copy down is this part right here is fine, but let's write down determining bond types, okay? So basically, we're looking at this is the difference in electronegativity. And I'll get out of your way here. We're just going to say the difference in electronegativity, we're going to take the bigger number minus the smaller number. Okay, that's all. And you know what? We don't even, I'm not going to get you to copy this either, because we're going to do some, we'll go back and do the examples with the 3 that we did. Okay. I'm just going to pause it here. And I'm sure you still have a few more questions here, but we'll get to that in a second here. But how do you decide if it's ionic or molecular, polar covalent, non-polar covalent, yada, 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 all that stuff? And the answer is, well, you're just going to basically do, you know, this formula here, or what, I don't know if it's really a formula, but you're basically just going to look at the difference in electronegativity and how large that number is. You know, if it's really large, then it's probably ionic. The difference is big. If it's 0, if the difference is 0, it's probably non-polar covalent. And if it's slight difference, well, I'd say it's probably polar covalent. Okay. Now, let's go back to our examples. I know there's some down here. We could do those as well. It doesn't matter. But if you think of any metal and non-metal and you subtract the difference, that'll tell you probably, you know, for the most part, it's ionic. Right? But let's go back to our examples here. I know I said I wasn't going to do this, but you know, if we look at this here, if we're trying to find the difference in electronegativity, if you want to go back to this part here, we would take 3.2 minus 0.9, and that's 2.3. Oh, come on. So again, if we're looking at the difference here, like I said, NaCl, 3.2, 0.9. If we look at the difference there, it should be 2.3, yes? So 3.2 minus 0.9 is 2.3. That number is fairly large. So there's going to be probably a good chance that it's going to give and take electrons, or be ionic in this case. And I know you have a question. It's coming. Okay. What's your question? What are you going to ask me? Come on, somebody. Emily, I know you have a question. What's the question you're going to ask me? What? Yeah. What's the cutoff, right? Exactly. That's exactly what you're wondering. You're like, everyone's wondering, what's the number? What's that number? I'm not telling you yet. Okay. If we go back to this example, if we go back, let's see here. All right. Now, if we're looking at hydrogen, we did this 2.2, 2.2. The difference here is 0. Okay, so non-polar. In other words, there is no difference there, and we'd share these electrons equally, right? So that's what's going on with the hydrogen in that case, or an N, or OO, or FF, BR, II, doesn't really matter, because both those numbers are going to be the same, of course, and you're going to end up with 0. What if you're doing polar covalent? Well, let's take a look here. I think we said, what, H and Cl here. This was 3.2 and 2.2, and of course, that's a net of 3.2 minus 2.2, that's 1.0. Okay, well, that's not big enough difference to gain and lose electrons, but it's definitely a difference. So we're going to have some elements that are not sharing electrons equally, of course, and that's why we get this little bit of a negative charge and a little bit of a positive charge, okay? A little bit negative, a little bit positive. Well, we have to remember this is not, most certainly not ionic, right? We're just not sharing the electrons equally, all right? Good? Everyone's got that if they need that, okay? So that's how we can subtract them to find out what the difference is and decide kind of what they're behaving like. Now, here's kind of a chart for you. You don't need this elaborate of one kind of thing or whatever. But before we get too crazy here, just before you start copying, it says difference in electronegativity. It goes from 3.3 to 0. Why does it start? Why is it only 3.3 here? Why is that? We talked about earlier. Yep. Exactly, right? Biggest one is 4, fluorine. The smallest one is 0.7, yes? Noble gases don't want to react, right? So when we're looking at compounds, you wouldn't include a noble gas in there because the noble gas is stable by it. It's not going to want to react with anything. So the biggest difference we could possibly have is 3.3. Yes, 4.7. 3.3 is the difference. And then we go all the way down to 0 here. Okay, I'm going to let you copy this in a second. Now, 3.3, 0, yes? How do you think they came up with the number 1.75? Basically what they're saying is, hey, this stuff here is ionic in this section here, up to there, and then this stuff here is basically what we would call molecular or covalent or sharing. How do you think they came up with 1.7? 3.3 to 0. How do you think they came up with 1.7-ish? Huh? It's in the middle, yeah? Okay, so big scientific experiment there, yeah? All right. Now, what you have to understand about this chart, I know you want to copy here, is look, this is, as with everything in life, this is kind of a sliding scale. So just because, what, you know, right here, if I had francium and fluorine, is it going to be ionic? Yeah, okay. And as I start to go this way, okay, as I get closer and closer to this number here, they might do a little bit. What happens if it's 1.7, Mr. Bachek? What happens if it's 1.7? Because that's in between the two. Okay. Well, then I'd say probably a little bit of both. Okay. So it's probably acting a little bit ionic, maybe a little bit covalent, polar covalent. Okay. So it's a little bit of both. And you're, what happens when I get the question and it says 1.7? You won't get that question. All right. Don't worry about it. But you know, you have to understand that this is just kind of a sliding scale. All right. So yeah, it's probably less ionic, getting closer to sharing perhaps. Probably here, could you have something that's a little bit more ionic maybe there? Possibly, yeah, you could. Okay. But again, we're talking about probably sharing very unequally, by the way. Here, if you're right there, you're probably sharing very unequally. Okay. Very unequally. And then, you know, like I said, as you get closer and closer to here, you start to get more sharing very equally. Okay? Does that make sense? So it is a scale. It's not to be like, you can't say, hey, 1.7 and above is ionic and 1.7 below is polar. It's a little bit of give and take here. Okay? So I'm going to stop talking and let you guys copy that. Now, I'm going to tell you right here, as we move this down, okay, this non-polar covalent, just pay attention for a second here, I'm going to let you copy, that has to be 0, okay? Non-polar has to be 0. You notice it says slightly polar covalent between 0.5 and 0, okay? That's true, it's slightly polar covalent. Apparently there's been research done that says if the difference is about 0.5 or less, that really doesn't have a significant effect on the molecules, all right? So what that means is they're probably still sharing almost equally, okay, almost equally. They might be very, very, very slight negative end and a very, 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 very slight positive end, okay? But we're gonna go with slightly polar covalent. You don't have to memorize that, okay? Polar covalent from here to here, from 1.7, oops, definitely to 0.5, even, like I said, you could even kind of venture a little bit over this way probably as well. It's still going to be polar covalent, maybe slightly, but that slight thing doesn't really matter a whole lot, okay? And then from 1.7 to 3.3, that's the section where we talk about mostly ionic. Notice it says mostly ionic, right? Because there's going to be a little bit of give and take there, okay? I'll let you copy that. That's kind of your deal with that chart there. Again, 1.7 is kind of a reference number, but it's not set in stone, so just kind of take that a little bit. But if the electronegativity is really large, we're going to get ionic. If it's a little bit less, of course, we're going to get polar covalent. And then we get down to non-polar covalent. That's kind of the ones that we use for that, right? That should be that. Good. Perfect.